Afternoon. Good afternoon, ladies and gentlemen. Ladies and gentlemen, please take your seats. Distinguished guests, friends, and colleagues, pick a star in our galaxy that is about 5 trillion miles or so away from us. Imagine that we want to measure the distance to a precision of better than the width of a human hair. That's what they advertise in Caltech website, for instance. That is, we demand a precision, something like that. Keep going, keep going, keep going, keep going. So that's the kind of, he's counting the zeros, but that's okay. So LIGO has been able to measure changes in length, as our speaker, Dr. Fritzel, will tell us, with this kind of precision. It's one of the greatest physics and engineering feats ever accomplished by humans. Quite rightly, it has got a lot of press, the Nobel Prize, and more to come, and much more. This kind of work is greatly uplifting because it's a wonderful testament to human ingenuity. But it wasn't easy. It took enormous effort and dedication of some 1,200 people from 100 institutions and 18 countries, not to mention some $500 million or a bit more than that of research money, and time and perseverance that had to counter a number of naysayers. How much perseverance did it take? This is the picture of our speaker today, more or less. And this could have been his picture when Rainer Weiss at MIT conceived this idea some 50 years ago. That's really not his picture, but it could have been his, and so I block it out a little bit so he doesn't get too upset. But you get the general idea that I'm trying to make. It was the accomplishment of almost 2 successive generations of scientists. Instant gratification clearly was not the operative philosophy. So before we invite the speaker to tell us the story of this monumental work, I have 2 important things to do. One of them is to introduce Jeff Lynford, who will tell us more about Peter, that is our speaker, about the history of the Lynford lecture and Tandon and all that. Jeff is the president and CEO of the Educational Housing Services and the vice chair of the Port Authority of New York and New Jersey. This is a gubernatorial appointment. He serves on many boards, which I will not take his time to tell you, including the Board of Overseers of our school. He is a former trustee of NYU and of the Polytechnic University, which is the previous name that the school had. Most importantly, he is the husband of Tandra Lynford, who is sitting there, herself an accomplished psychotherapist working with children. Together, Tandra and Jeff support many worthy causes in New York City and also worldwide. I will cite only one example of the latter: their continued commitment to young students in Ethiopia. It's people like Tandra and Jeff that make the world go round in some ways. So for all this, Jeff and Tandra, thank you very much. Tandra. Jeff will come on stage and everybody will be able to see his face. But Tandra, would you kindly be recognized by standing and turning your face that way? Thank you. Thank you very much. My last task is to thank a number of people. First, the speaker himself. Peter, thank you for agreeing to come give us this talk. I know how busy you are, especially now when everybody understands the importance of the work that happened. My thanks go to panelists, Dr. Markov, who is sitting right here, who is the Walter LaCroix Professor of Physics at Columbia, and my own colleague who is sitting next to him, Andrew McFadden, from the physics department at NYU. Many thanks also to Ms. Lindsay Boylan, who is sitting right there in the middle, the Executive Vice President and Chief of Staff of the Empire State Development, for her participation. And to all other dignitaries and friends that are here in the audience, my sincere thanks for being here. I will now leave the rest of the proceedings in Jeff's capable hands. Ladies and gentlemen, please welcome Jeff Lynford.
Thank you, Srini. Yeah, you made me look good in front of my bride, so I want to say hello to your bride. You want to please stand? This is the force of power behind Srini, his wife, Sudha. So the slate is clear, Srini. The professors, David and Gregory Chodnovsky, and my wife, Tandra, and I welcome you this afternoon to the 2017 lecture, LIGO and the Dawn of Gravitational Wave Astronomy, featuring presentation by Dr. Peter Fritschel, who I'll now call Peter since we've become such good friends, from the renowned Kavli Institute of Astrophysics and Space Research at MIT. Also, I'd like to recognize at this time an outstanding public servant who has made a special journey to be with us today, CEO of the MTA, Pat Foy. Where are you, Pat? Raise your hand. Ah, there you are. Okay, Pat has been a tireless supporter coming to the last 4 or 5, and he's now in charge of fixing the subway. So if any of you have a complaint, and I'm sure none of you do, but if you have a complaint, we've locked the door, and Pat is not allowed to leave until you fix the L, the M, the Z, whichever one they want to talk about. Okay, Pat? Thank you. Our program today will include 5 parts. First, an opening of the proceedings by Governor Andrew Cuomo's special representative, Ms. Lindsay Boylan, Executive Vice President, as Srini said, of the New York Empire State Development Corporation. And she's going to tell about the special connection to the Lynford lecture that the Cuomos have. Second, there'll be a presentation of the plaque by the brothers Chodnovsky to our speaker. Third will be Dr. Fritschel's lecture. Fourth will be a conversation in these 4 chairs with Dr. Fritschel and 2 our guest physicists, Professors Andrew McFadden, raise your hand, of NYU, and they call him Zabi Marka, Dr. Zabi Marka, professor at Columbia University, who also worked on LIGO. And they are going to serve as interlocutors and ask questions of Dr. Fritschel based on his remarks and his experiences. Lastly, any students that want to stay after the proceedings and talk individually with our interlocutor and speaker, that's wonderful. They like to talk to students. Students are why they exist. But we have a hard stop at 5:30 because we double booked the auditorium. No, seriously, there'll be another group coming in, so we'll say thank you at 5:30. And over the last 2 decades, the brothers Chodnovsky have been responsible for selecting and inviting the best and the brightest. And they've had a variety of speakers before these speakers were recognized as for their important contributions. For example, in 1999, Craig Venter was here, and he, as some of you know, decoded the human genome. And then the following year, in February, he actually stood with President Clinton on the White House steps to announce it. So we were very happy to get him here before the world understood, and now we have Peter. Now, we invited Peter before the October 3rd announcement of who got the Nobel Prizes. And one of his mentors and PhD dissertation advisor was one of those 3. But behind all 3 great old men are the next generation of physicists, and Peter is one of them. And he's going to tell us today about his contributions and his work for the last 25 years. That's why that photograph was up. And so let me give you some background on Peter. He hails from Watertown, South Dakota. Who's the senator from South Dakota? I know they have one. That's not Thune. Is that North Dakota? Am I putting you on the spot?
I think it is.
Thune? Okay.
I've long since.
Well, we want to say how ecumenical we are here, and we take people from all over the world, even MIT and South Dakota. And he migrated east to Swarthmore, where he graduated with a BA in physics with honors in 1984. And then he traveled north to Boston, where he earned his PhD in physics at MIT. And that was the turning point in his life and his career, I would argue, because he wrote his 1992 dissertation, and it was entitled Techniques for Laser Interferometer Gravitational Wave Detectors. And 25 years later, he's here. So how did you know 25 years ago, you can tell us when you come up, that you were on the right track? And I think that one of the important things that students can learn from this, now Ryan, where are you? She's a senior. I've been mentoring her for the last 2 years. I want to embarrass you. But what I've been saying to her is get the right mentor. Now, I don't know how you find the right mentor. I'm not he. But Peter found. So listen how Peter found his mentor and then his life's calling. Okay? Peter, you can talk about that. So today, Peter is the senior research scientist at the Kavli Institute and chief detector scientist on LIGO. I thought that was a fascinating chief. I almost said detective scientist, but so you can talk about that too. But most importantly, lately, he has been the co-chair of the writing committee that published the astounding findings in the February 12th, 2016 Physical Review Letters about observations of gravitational waves from a binary black hole merger. Now, I come from Wall Street. I know what a merger is between pharmaceutical companies and banks, but between black holes, that's a different type of merger, and we're all very interested to hear. And this paper is the result of 1,000 scientists and engineers from over 100 institutions located in 18 countries. And think about the logistics of organizing something like that. So, most recently, in recognition of his work, he and 2 other physicists were named the winners of the 2018, once again, we're ahead of the curve, Lancelot Berkeley Prize for, quote, detection of oscillation in the fabric of space-time. So, congratulations. Now, I'm going to turn the podium over to Ms. Lindsay Boylan with her message of greeting from the governor. Lindsay.
Thank you so much, Jeff, for that kind introduction and for your generous support in the creation of the Lynford Lecture, and Tandra, yours as well. It feels particularly apropos to be here now on behalf of Governor Andrew Cuomo. As Chief of Staff at Empire State Development, the state's economic development arm, I work for the governor in support of his agenda, both for jobs and to continue to transform the economy for all New Yorkers. I'm regularly tasked with briefing the governor on what I would call complicated projects and nuanced ideas. Just yesterday, for example, we were talking about an announcement of a new kind of glass called Valor Glass, which will be transformed in the life sciences industry to produce better, safer packaging for pharmaceutical products at Corning, upstate. This glass will, as I said, help transform the industry. It's a great news story for the state, $100 million of private investment in upstate New York with Merck and Pfizer as clients already, and over 200 jobs promised in manufacturing of this product in the coming year. So that seemed complicated to me to explain to the governor. Delamination was complicated enough. Boy, am I glad I did not have to explain LIGO and the dawn of gravitational wave astronomy. I think I might lose my job really fast. But I will promise to try and summarize for the governor tonight's conversation in the panel after it's over. It really is an honor to be here. Many esteemed individuals have taken the stage, Bonnie Bassler, Daniel Kahneman, and Hillary Clinton, just to name a few. The first ever Lynford Lecture, the inaugural event of what would become such an important event here in Brooklyn, took place in 1998. The public official who introduced that lecture was none other than the late Mario Cuomo, former governor of New York. He spoke in the same auditorium where we find ourselves today, and he spoke on a night where the topic a la mode was a little idea called string theory. Ed Witten, professor of physics at Princeton University, addressed the room with a lecture entitled Adventures in the Quest for Unification. He sought to bridge the gap between quantum physics, which, as of course you would all know, describes the nature of things at the smallest scale, and relativity, which obviously focuses on the interplay between space, time, matter, energy, and gravity. Professor Witten posited his hope that one day the space-time continuum would ripple in such a way these two theories of the universe could be brought together in one unified theorem. Today we have that evidence, and there's certainly an unintended symmetry in my being here this evening on behalf of Governor Andrew Cuomo, 20 years after his father stood in this very room. We've come full circle in such a meaningful way. You know, I took a class in general relativity at Wellesley College. Though I've devoted my career to economic development and government, I can assure you that the course has come in handy today. I actually reached out to my professor knowing that I was coming here, so it was very helpful. Now, truth be told, it was the one class at Wellesley that I took pass-fail, but that doesn't really matter for today's purposes. Nonetheless, I'm here to send the governor's good wishes in support of the advancement of big, groundbreaking ideas and advancing them in the state of New York. New York is the first in the Northeast in total number of STEM graduates annually, approximately 38,000 degrees at all levels, associates to doctorate. We're second in the U.S. for number of top-tier research universities, for highest number of residents who are scientists and engineers, and generating both mathematical and physical science degrees. New York University plays a tremendous role in that ecosystem. A college degree today is what a high school degree used to be yesterday. It is required even to get your foot in the door for many 21st century jobs. And NYU, including everyone in this room, is part of why New York has one of the most diverse, skilled, educated workforces in the country. Just a few weeks ago, we announced the Veterans Future Lab, a technology startup hub with NYU Tandon School of Engineering that provides mentorship and support to early-stage startup ventures founded by United States military veterans. The Veterans Future Lab, located at Industry City right here in Brooklyn, will offer premium subsidized incubator space and advance veteran entrepreneurship and early-stage startups through access to mentors and industry leaders, community events, and other entrepreneurship-specific services. I want to wrap up by talking just a little bit about people because New York's greatest asset are New Yorkers. This room is full of movers, thinkers, creators, builders. You're at the cutting edge and the frontier of all the things we know and all the things we have yet to learn. And New York is very proud and excited that you're here today, even if you're coming from Boston. Thank you.
I will be very brief. I will just present to Peter the 2017 IMAS Award with the following citation. For leading the LIGO team in harnessing the power of LIGO detectors to map the universe. Thank you very much for coming.
Thank you very much.
Picture with Conrad is ready and Peter. Okay.
We can go near Gregory.
Well, he was a little busy. Yeah, let's go near Gregory. Yeah, good idea. We're going to come near you. Why did I think of that? That's where you're lean, I guess. Thank you. You're just going to go.
Let's see. I wonder if I need a little AV help to get to where I want to be. Can close this. Yeah.
I guess,
Exit that guy.
yes, that one is gone.
Yeah. And then mine
Yours is what is it called?
should be down in the bottom somewhere. Yeah. There we go.
Yeah,
Let's
okay.
get to the first page. And just do a show. Okay, this should work. And yeah, I guess this seemed to work pretty well, right? How is the audio for everybody from here? Good, great. Good. All right. Well, thank you, Jeffrey, for the introduction. Thank you, David Gregory, for the invitation. It's an honor to be here, and I hope this is a lot. It was a lot of fun putting this together for this audience, and I hope you'll enjoy it, and not just the talk, but the discussion we're going to have afterwards. So, yeah, let's get going. I think so. Let me start by picking up on something that Jeffrey said. So, I mean, I'm here today, talking in front of you, but really representing the work of it's characterized typically as 1,000 scientists. Of course, that 1,000 number is something that grew over time, obviously. When I started with this project 25 years ago, it was one among, we could count us in dozens at that time. Even within the U.S., even smaller than that. Which for me actually was really part of the attraction, getting in very early on something. I mean, I had no idea that it was going to, I was going to stick with the field for 25 years. I have no idea, or that it was going to take that long or anything. But for me, it was very attractive to start on this project that had this, very, very, glorious goal. But there's, just a small number of people working on it. I was turned off, sort of by the big high energy experiments that were going on, and I didn't want to join that kind of big collaboration, which of course we've turned into now. But for me, getting in at the beginning, even though I obviously had no idea what it was turning into, was really one of the attractions of it for me. But anyway, today I'm representing, those 1,000 people in everything that I say. So let's, as mentioned, so obviously gravitational waves, LIGO, it's been in the news in the last couple of years. So just a kind of a quick recap. In February, on February 12th of 2016, newspapers all over the world had on the front page the first detection ever of gravitational waves, all languages, and the detection had actually been made in September of the prior year, but this is when we announced it. I guess we announced it the day before, and so it was on the front pages of all the newspapers on February 12th. And not only, I think what was so spectacular was not only the first direct detection of gravitational waves, but it was detection from something really, really fascinating, which was two black holes that had merged into a single black hole. Following on the news, October of this year, of course, we had a few other black hole detections in the intervening time, which you may not have noticed. I mean, they were covered in the press a little bit, certainly not big front page news, but we had a couple of others that we announced. And then, of course, in October 3rd of this year is when the Nobel Prize Committee announced that they had selected 3 laureates from honoring them for the gravitational wave detection, as they said, to honor a discovery that shook the world when it was announced on February 12th. So that was my mentor, Ray Weiss, over there on the left, who is one of the original conceivers. And so these 3 folks were chosen for the prize because they're sort of amongst the 3 early leaders in the field. Ray Weiss in terms of conceiving of the experiment. We'll talk a little bit more about that. Kip Thorne on the very right in terms of conceiving some of the theory behind the experiment. Why is this an interesting thing to pursue from the theoretical side? And Barry Barish in the middle for really getting the actual project really kind of off the ground in the early 90s. Just a couple weeks later, after that Nobel Prize announcement, was another big announcement, again, often front page news, where another detection, now not 2 black holes that merged, but something for a lot of people was even more interesting, which is the gravitational waves from the merger of 2 neutron stars. And I'll get in what neutron stars are as we go on. But that also made very big splash just very recently. So those are big news events that have been out there. We've also seen that gravitational waves have started to enter the mainstream society in other ways. So this is a advertisement that was found in the New York City subway system, not long actually after the February announcement, and it's essentially implying that it's harder to find an apartment in New York City with a walk-in closet than to discover gravitational waves. I don't really agree with that, but you all are probably pretty familiar with the second part of that, the New York City apartment, and maybe by the end of this talk you'll be more familiar with the first part too, so that you'll agree with me that actually detecting gravitational waves is harder as well. So what I want to do now for the rest of this talk is really go in and get behind the headlines, tell you, what are gravitational waves, What is it that we've detected? Why are they so interesting? How did we do it? How did we make these detectors to do it? So they go through a historical perspective. And of course, the story starts 1.3 billion years ago, give or take a few 100 million years. We actually don't, we often say 1.3 billion years, but we don't pin it down terribly accurately. So it's plus or minus a few 100 million years. When there were a couple of black holes that had been orbiting around each other, of course, for many hundreds of million years, but at that point they got close enough together where they started to merge. You had one black hole that was 36 times as massive as our sun, another black hole that was 29 times as massive as our sun. They're orbiting around each other. This is a simulation of that. That's actually slowed down a great deal. So this is, I guess it's slowed down 100 times. This, what you're seeing actually just lasted a fraction of a second. And eventually merged into one single black hole that had a final mass 62 times the mass of our sun. In the process, it radiated, if you did the math of those numbers that were on there for just a short period of time, you're missing 3 solar masses at the end. So actually 3 solar masses worth of energy were radiated in this process. So you started, with 65 solar masses worth of material at the beginning. As they were merging together, they radiated energy in gravitational waves, and so the object that you had at the end only had 62 solar masses worth of energy. So it's an incredible amount of energy just radiated in gravitational waves. And when they were going sort of as fast as they would around each other before they started to merge, they were actually going relative to each other at about half the speed of light. So just an incredible thing to think about, something that's tens times as massive as our sun, moving close to the speed of light. Quite an incredible thing. So these gravitational waves, 1.3 billion years ago, started propagating out in the universe. We're going to speed up the history there a little bit and go not to the present, but 400 years before the present, where we first start to get some understanding of gravity. Of course, that comes from Newton, right? And he came up with, in the 17th century, his universal law of gravitation, which of course says that there's a gravitational force between two massive bodies. That force is just proportional to the two masses themselves, so M1 and M2 in this formula, and it's also proportional inversely to the square of the separation between those two masses. And that was his universal law of gravitation. Now, one of the things that was sort of odd about that, in fact, Newton worried about this, is how does mass 1 know about that it's supposed to be attracted to mass 2? How does it know that mass 2 is out there that needs to be attracted to it? But he didn't have a solution for that, but it did actually bother him. So we didn't actually have a good understanding of that until the next big hero of gravity came along, which of course is Albert Einstein. And he explained gravity in his general theory of relativity as a warpage of space-time. So rather than talk about forces between the two masses, he talked about each mass as warping the space-time in its environment, and thus the other mass would be responding to that warpage of space-time. So the simple sort of explanation of it is that matter tells space how to curve, and then that curvature correspondingly tells matter how to move. So rather than talking about forces between two bodies, you're talking about the curvature of space and how matter changes the curvature of space. And that's expressed in his general theory of relativity in this nice, very simple looking equation that's in the blue blob there. Very simple looking, it turns out to be incredibly difficult to solve. Only in very simple cases can it really be solved without using computers and doing numerical solutions of the thing that have only very recently been produced. So let's look a little bit more at that idea of mass in general relativity, that mass is warping or bending space-time, starting with sort of our Sun-Earth system, where the sun provides a relatively large warpage of the space around it. And here the space is depicted as a two-dimensional grid. Of course, that's just a representation of true 3-dimensional space, just because that's what we can easily draw. So we're seeing the warpage in a two-dimensional plane, but it's just sort of a representation, of course, of three-dimensional space. But then the next thing is, and those two bodies are just, you can think of them as static, so that there are these sort of static deformations around them. But then the next aspect of it, which Einstein also came up with, was that if these masses are now not static, but let's say you have two masses that are orbiting around each other, that those deformations of the space are gonna propagate out, and you're gonna form gravitational waves. And you can think of those again back in this sort of space-time picture as little ripples in the space-time fabric, radiating away from the original objects. Originally, actually, Einstein was very ambivalent about this prediction of gravitational waves in his theory. So while he formed his complete picture of general relativity between sort of 1915 and 1918, I think the original gravitational wave prediction, or the outcome of his calculations, was incorrect, and he had to correct it later. Shortly after the completion of general relativity in 1918, another physicist came along, Schwarzschild, and he looked at Einstein's equations and realized that the equations were consistent with having a lot of mass in a very small volume, so much so that light couldn't even escape from gravity, which of course is what we now know as a black hole. At the time, they called them dark stars. Einstein didn't really like the idea; he was just sort of uncomfortable with it. As I said, he actually, vacillated several times about whether gravitational waves were a byproduct of his theory of general relativity or not. And in fact, in his original papers in 1916, he published a paper later in 1936 where he retracted the claim that gravitational waves existed. Shortly after that, he retracted his retraction after discussion with somebody else that pointed out that his retraction was in error. And then he was kind of silent on the subject for the rest of his life, actually, on gravitational waves and black holes. But actually, the whole idea of whether gravitational waves were real would still remain kind of controversial within the physics community up until about 1957, when there was a conference at Chapel Hill that it was just sort of a watershed moment that people worked it out at this conference and realized there's sort of when the question was, is it just a mathematical entity and it doesn't really correspond to anything real physically? But at this conference is when they really, finally worked out, and everybody was convinced that yes, gravitational waves are real, and they're real physical things. And that's sort of the history of the theory behind gravitational waves. Me being an experimentalist, we'll point out here at the end that in the end, experiments and observation will have the final say as to whether what our theories are correct or not. So with that, I'd like to turn to the history of the experiments and observations surrounding gravity, general relativity. So the neutron stars that I mentioned at the beginning of the talk, and what we'll get back to, were first proposed in 1934. And so a neutron star is basically, you can think about it as just a giant nucleus. It's a star maybe as massive as our sun, but just composed of neutrons, so it's much, much denser. You can think of it as like a giant nucleus. And then rotating neutron stars were proposed as an idea in 1967, and the idea there was that they would, if you have a rapidly spinning neutron star and it has a large magnetic field, it's going to emit a lot of electromagnetic waves, radio waves, in a pulsating fashion. That's why it's called a pulsar. So actually later in that same year is when the first pulsar was observed by Bell and Hewish. And then in 1967 as well is when John Wheeler first coined the term black hole rather than dark star. Around the same, a couple of years later, was when we had our first attempts at trying to detect gravitational waves. So Joe Weber was at that Chapel Hill conference, and when people finally decided, yes, gravitational waves are real, and he went off and tried to make the first experiments to detect them. He did it using a big bar of aluminum that you can see here, a big cylinder of aluminum, that if a gravitational wave went through, his idea was that it would kind of set it off ringing. like a bell rings or a nice wine glass rings if you tap it. And he actually claimed that he detected gravitational waves back in 1969. And then many people tried to replicate his experiment and so on, and it was never nobody ever had agreement that he actually detected. So those original claims have been discredited. And indeed, I mean, the instrument that he had back then was not nearly sensitive enough, really. Now that with our current knowledge, we know it's not nearly sensitive enough to detect something. Then the first black hole was discovered in 1971, and not with gravitational waves, of course, but by observing star systems using X-rays. By observing binary systems with X-rays, you can determine what the components of the system are, and you can infer that there's a black hole in that system. And the first one of those that was discovered was in 1971. And then, as another kind of watershed moment, when the first pulsar had been discovered in 1967, and then there's a binary pulsar system, so two of these stars together orbiting around each other, that was first observed in 1974 by Holson Taylor. And what they then started to do was to measure the period of that pulsar over long periods of time. So they monitored it over several decades. And the idea is, if that system is now two neutron stars rotating around each other, it's going to be giving off energy in gravitational waves. And so its orbit's going to be slowly decaying. They're going to get closer and closer together. And that orbital period can be monitored by measuring these radio waves. So they're not measuring gravitational waves, but they're measuring radio waves. But through measuring radio waves, they're monitoring the orbit of this system. And they see that orbit is decaying at exactly the rate that you would calculate if it were losing energy through gravitational waves. So that was the first experiment where we call it an indirect proof of gravitational waves. You're not measuring gravitational waves directly, but you're measuring their effect. And for that experiment, the pair won the Nobel Prize in 1993. So getting back to Einstein's ambivalence about gravitational waves, and eventually he recognized their existence, but thought that they would never, we would never do anything with them. They'd never be important in physics or in astrophysics. And you can see why at the time. This equation here at the top is representing the luminosity or the power in gravitational waves. And there are a couple of factors in there that are very important in order to have a significant power, luminosity, in gravitational waves. One is the last one, which is where v is the velocity or the relative velocity of the source. And to get something, with a large number there, you need a velocity that's large compared to the speed of light. So v over c to the 6th power. So you need something that's moving very fast. The other factor is the second factor there, where you've got a capital R in the denominator squared. R is the compactness of the source, or sort of the radius of the source. And that, of course, to get a large luminosity, need to be small. So you need things that are very compact, moving at velocities that are approaching the speed of light. As we saw in the last few decades, we learned about neutron stars and black holes, but Einstein didn't know about those, and he was never really comfortable with the idea of black holes. So you can see why his sort of ambivalence about gravitational waves was warranted at the time. But I think what's really interesting is that even so, his theory of gravitational of general relativity can be very well explained. All of the features of that can be very well explained by the observations that we've made since then. Okay, so moving on to actual detection of gravitational waves. So they're very faint. What I put up here over on the left is one of the more simple expressions you can form for the size of gravitational waves from a fairly simple system of just two masses orbiting around each other. And what it says is that the gravitational wave, the little h, is the parameter that's characterizing the amplitude of the gravitational wave. And that little h is something we'll get to in another couple of slides, but it's the strain value of the gravitational wave. And what that says is proportional to lots of constants. There's a speed of light to the 4th power in the denominator, which of course is a big number. That's why gravitational waves are very, very small. but it's also proportional to this big capital I, which is the quadrupole moment of the system, which basically just depends on the mass and how far apart the masses are. And it's actually then the double dot's the second time derivative of the quadrupole moment. So like I say, for just a system where you have two masses, that expression is fairly easy to work out, and that's given by the line on the bottom here. So what you see is that this h term, or the amplitude of the gravitational waves, the amplitude that kind of characterizes it for something that's 30 times the mass of our sun, so something quite massive, that is at a distance of here I've used megaparsecs, which is rather than light years, so the 400 megaparsecs is about the same as 1.2, 1.3 billion light years away. And when they're orbiting around each other at about 50 times per second, you're going to get a gravitational wave strain, here on Earth, of about 10 to the minus 21. So these are the really small number that Jeffrey put up on his first slide. And the waveform that's going to come out of this is basically as shown in this plot. So it's basically a sinusoid, right, that's oscillating tens of hertz. The frequency is kind of slowly increasing, and the amplitude is slowly increasing over time as well until the two objects merge. And that's when the amplitude of the wave has the maximum. The two objects have started to merge. This is something that we call a chirp, and we tried to get the audio for this going with the audio guy, but we didn't quite get it there. But it's you might have heard it in the news. It's sort of a whoop kind of sound if you turn the waveform into audio, right? Which of course it's not audio, but if you turn it into audio, that's what it would sound like. So that's kind of the waveform that we're looking for, and again, the scale of it is just so small. But as Jeffrey said, this mentor of mine, Ray Weiss, started thinking in the early 70s, but maybe it's still detectable. Maybe there's still a way to make it detectable. So this slide is showing, okay, so what's the actual effect of that gravitational wave, of a strain of 10 to the minus 21 here on objects on Earth? So what I've tried to depict up in the upper left is a grid. You can think about it as a grid of particles, so sort of mapping out space-time in a grid. And if a gravitational wave is propagating out of that, so towards you guys, what it's going to do is going to distort that grid so that on one cycle of the wave, it's making the grid shorter in one direction, longer in the other direction, right? And then on the other cycle of the wave, that gets reversed, so the grid gets longer in one direction and shorter in the other. And that's the effect that we're going to capitalize on to try to measure gravitational waves. And we're going to do that using an interferometer, what's called a laser interferometer. That's what's depicted on the lower right. And an interferometer is well designed to measure very small distance changes like that. So basically, we're taking a laser, which is in the, does it have a little laser pointer? Yes. A laser that's sent down these two arms, so you can think about the laser beam, probing these two orthogonal directions. And the laser light gets split in two, and when it comes back, it interferes, and then it's very sensitive to very small changes in displacement is going to change the interference pattern at the output. And that's the basic idea that Ray Weiss proposed. And this is a diagram from just an internal MIT technical note that he wrote about it in 1972, actually, and he drew this up. And this is drawn as just a laboratory scale experiment. But what we ended up, what LIGO ended up being has many of the features that are in this original drawing from 1972. But even at the time, he realized that, even though this is sort of a laboratory scale instrument, he realized at the time that you need to make the thing really, really big, right? So the feature of the gravitational wave strain is such that the change in distance that you're going to measure with the interferometer scales with the length of the interferometer, okay? So the change of distance that we're going to measure is that gravitational wave strain amplitude times the length of the arms. That's why we make the arms so long, 4 kilometers long, or even longer if we could. So what that means is if we're looking for our strain of 10 to the minus 21 over a baseline of 4,000 meters, we're looking for distance changes that are still very, very small, 10 to the minus 18, or 4 times 10 to the minus 18 meters. But by making the thing, much, much longer than just what an individual laboratory could hold, you're starting to make it now detectable. At least that's the idea. So why is it so hard? Why? Obviously, it sounds like it's really hard, right? The numbers are really small, but why is it actually hard? So the enemy, in terms of pulling this off, is really various kinds of noise sources that interfere with measuring a signal of that size. So just what are a few of those? And so that's, this could be a whole, talk in itself, just talking about the various noise sources. But so what are some of those? The laser itself that we use, of course, has fluctuations of its amplitude and its wavelength that we have to control. The test bodies, or the masses that we use at the ends of the arms, we need to isolate them very well, obviously, from seismic noise. Otherwise, they'll just be shaking too much. Heisenberg uncertainty principle, probably you've all heard about that. So quantum uncertainty comes into play when you're looking at making measurements at this level, and those kind of those show themselves both as what we call shot noise in the detection of the light, and also as radiation pressure noise, just photons buffeting the test masses themselves. You also just have thermal motion of the masses. Just because you're at room temperature, they're going to be sort of bouncing around on their own, something also called Brownian noise. Another thing that you have to worry about is just the light itself. There's going to be a little bit of air particle on those long arms that we talked about, and light is going to scatter off of those and create fluctuations. So all of those things you have to deal with. But we thought we had a design that we could go forward with, and thankfully the National Science Foundation funded us to go forward with what we think was a very bold experiment. And so that was the start of LIGO, we got started in around 1990. And so the National Science Foundation funded us to create these two sites, one in Louisiana State and one in Washington State. This is Louisiana on top and Washington on the bottom. And they each have these 4-kilometer long arms. They're identical detectors, essentially. The environments they live in are kind of fairly different, but the detectors themselves are fairly identical. And we had to, design them to try to measure changes in the arm length of that order, 10 to the minus 18, 10 to the minus 19 meters. Let's see, I need to click on this. So this is a little video now going in and taking a tour of the observatories. This is the Hanford Observatory from the air. The rest of it is now using the CAD, the computer models of the interferometer. We'll kind of look inside and see what they look like. So these are some of the vacuum chambers that the components of the interferometer are in. And we're going to get a little bit of a tour of that. So the laser beam comes in, and you're going to see it trace the path out. Now, of course, in reality, the laser beam, right, is always on in the instrument. So you don't see it do this, of course, but it's just sort of tracing it out so you can see where it goes. All of these colored elements are mirrors that are elements of the interferometer. Another thing to point out is we make heavy use of something called optical cavities, resonant cavities. But basically, at this point, our input laser beam has come and is now being split into two, going down to the two arms by that BS called beam splitter. And now let's follow as the laser beam goes down the two arms. And what this animation is showing that beam going back and forth and getting brighter every time it does that. And what that's doing is representing this idea of an optical cavity where the light is actually building up many, many times in the arm in order to increase the sensitivity to gravitational waves. Now we're going to look in at what one of the mirrors or test masses looks like at the end of this 4-kilometer arm. And that's this object right here. So the laser beam is now bouncing off of that mirror, headed back towards the corner. And I think it now takes us back to the corner. So the two beams have traveled down the 4 kilometers, are coming back to interfere at this beam splitter again. Travels through a bunch of other optics on its way to the output of the instrument. And again, it's going to go through another sort of optical cavity before it gets to the actual photodetector here that is measuring the output of the interferometer. And then I think this depiction is showing, okay, now with the arms moving differentially, one getting shorter while the other getting longer. Now a little bit of the same thing in actual photographs rather than the computer simulation. So this is while the beam tubes were being built in Livingston. So the beam tubes are these they're stainless steel tubes. They're fairly big. They're about 1.2 meters in diameter, and of course the full 4 kilometers. And they're covered with concrete arches, just to keep them from the elements. Those big vacuum chambers that are in the corner station, made of stainless steel. We operate what's called an ultra-high vacuum system, which is a pretty good level of vacuum. I mean, not the world's best, but actually quite good, meaning there's very, very little air particles inside these chambers. Here is a photo of one of the mirrors or the test masses that's at the end of the 4-kilometer arm. Okay, so you can see it's fairly large. You might think it doesn't really look like a mirror to you, but what it actually has is special coatings that's very highly reflective for the wavelength of the laser light that we use, which is not a visible wavelength. We use 1 micron light, which is just beyond what you can see with your eye. So this reflects very, very well at 1 micron, but not necessarily all that well at visible wavelengths. That mirror is actually mounted, before it's been installed in the chamber, it was mounted, you see it over here, and it's mounted, and it's actually suspended from this piece of glass above it with some very thin glass fibers. And that's done to keep the noise of the system very low, but a very, very complex mechanical system. That mirror system is mounted to a vibration isolation system, mechanical vibration isolation system, that also is really quite state-of-the-art. There are a couple of stages. It's hard to see what's going on in this kind of photo, but there are 2 stages, and each of those stages has complete active control of 6 degrees of freedom of motion in order to suppress vibrations coming from the outside. This is the laser system. It's a 200-watt capable system, again, at 1 micron wavelength. And again, so this is a custom-made laser, of course, just for LIGO. Okay, so that's sort of the tour of the instruments. So let's get back now to those. We've now, I think, let enough time lapse so that those gravitational waves that were emitted at the beginning from those black holes have now arrived on Earth, or at least in September of 2015. And as I said, at this point, we've actually measured a handful of mergers of black holes. So the one that we announced in February of 2016, that was detected in September of 2015, was the first of those, but we've had several more since then. And again, this video is just depicting that journey of the gravitational waves propagating out from the source of the gravitational waves. And the reason I like this video, and I included it, is a feature that we're just about to see. So as the gravitational waves approach Earth, they're going to come in from down here eventually. Yeah, you can start to see them, sort of the green come in, and it'll get a little bit stronger. But what this is showing, and this is actually kind of the direction that our first detection came from, what this shows you is that the gravitational waves basically just go straight through the Earth. They don't get impeded by the mass in between from where they originally emitted to us. So very unlike, observations with telescopes that look at light, where, the things that are in between us and the original source will block the light. Gravitational waves are just going to go right through. So that's a very nice feature of using gravitational waves to study the universe. This is the actual signal that we got from that first detection of gravitational wave, of black holes merging together. So again, what we actually detected really occurred over about a quarter of a second, and we saw these oscillations. Obviously, it's not as clean as that chirp signal I showed in the theory part of the talk, because there's detector noise on top of it. But by analyzing this with the expected waveforms, you can pull out a lot of parameters. And again, you can see that what we detected in terms of strain was kind of this 10 to the minus 21 level that we started out with as our target. And again, the power that was emitted by the source at the very peak was just enormous. 4 times 10 to the 49 zeros after watts was the peak power emitted, which is actually graded. So it was over a very short time interval, of course, but at that peak power, it's actually more power than all the visible light in the universe at that time. So for a very, very brief instant, this source outshone everything else in the universe. So this is sort of depicting, as I said, we've discovered a handful of other mergers of black holes. The first one is this one over on the left. And what this is showing is the two of the masses of the two black holes before they merged. So the one that I started out with was 36 and 29, and then the others that we've detected are all in that kind of same range of masses of tens of solar masses worth of black hole mass. What's also shown over here are the other black holes that we've known about by these X-ray observations that I kind of mentioned early on. So the next thing is, before I move on, I'll also sort of end up by talking about the neutron star merger detection. But before I get to that, let me just briefly mention something that's a good thing to have, a good requisite for getting into that, which is talk about the fact that we're not just LIGO, we're starting now to get a global network of gravitational wave detectors. So far I've been talking about the results from LIGO, which is the two detectors in the US in Washington State and Louisiana. We also have a detector now that we're sharing data with called Virgo, which is in Italy. There has been another detector in Germany in operation for a while. It's called Geo 600 because its arm length is 600 meters. So it's much shorter, so it's not as sensitive by any means than the LIGO detectors or the Virgo detector. The Virgo detector is similar to LIGO. It's 3 kilometers long, not quite 4, but otherwise similar. Eventually, we're now embarking on, there's going to be one of the LIGO detectors installed in India, and they're just sort of getting started on that, but in sort of 5 to 7 years' time, that'll be operational as well. The Japanese are building one called Kagra, which is also multi-kilometer long. That one's a little bit different. It's going to be underground. So eventually we're going to have this network of detectors. People are also planning detectors in space, of course. Many nice things about going up into space. So there the arm length, rather than being 4 kilometers, is actually 5 million kilometers. Much, much easier to get lots of real estate up in space. But the reason I wanted to point that out was because what's important about having multiple detectors is to be able to better determine where the source is on the sky, where it's actually coming from. With just one detector, you don't really know where it's coming from because we're not like an optical telescope that points. It just we're more like an ear that hears anything from any direction. And so for these black hole mergers, this is a depiction of the sky, kind of on projected onto a sphere, and what these colored bands show are how we could localize where the source of these binary black hole mergers were with LIGO and Virgo, with the two LIGO detectors. So, for example, this big orange band. You don't need to worry about the multiple lines, but just sort of look at the whole orange patch, and we could localize. It's coming from somewhere in that patch, which is a pretty big patch of the sky. I mean, it's huge by the standards of astronomy. But when we add more, so this detection down here, one of our most recent binary black hole detections, we actually had Virgo, the third detector in Italy, contribute to this one as well, and with that we were able to pinpoint its location much better. So zooming in on that, we were able to, with just LIGO, we were able to localize it to kind of this large light green patch. But then by adding the Virgo data to the mix, we're able to localize it much, much better. And that turned out to be quite important, or it's something that's quite important for neutron stars. Because what's different about neutron stars is when neutron stars merge, you expect to get not just gravitational waves, but also light of all varieties coming from that. With the black hole mergers, with being black holes, you don't really expect any other kind of form of radiation coming from them. So, as we now know, we detected our first binary neutron star merger in August 17th of 2017. And we detected it with all 3 of those instruments, so we were able to localize it fairly well. And so we sent out notices to the astronomy world that we've detected this, and that we think it's kind of in this region of the sky. And so that was rapidly followed up by telescopes all over the world, and about 70 telescopes have observed the event since then. So just a reminder, right, about what neutron stars are. So what this is showing is something that's called a supernova remnant. It's called, this one, particular one is Cassiopeia A, which is about, this is a supernova that was in our galaxy that occurred about 300 years ago. And what a supernova is, right, is when you have a massive star, and when it finishes burning all the nuclear fuel, there's gonna be a combination of an explosion of the outer parts of the star, and then the inner core of the star is gonna collapse into a neutron star. And so what this image is actually a telescope image, or it's actually multiple telescope images, is showing the outer parts of that supernova still emitting radiation as it's propagated out. But then at the very center, I think it's this turquoise dot, is the neutron star at the center, which here is observed through X-rays. Okay, so that's just a little bit more background of what a neutron star is. And again, another thing we also like to say is the compactness of a neutron star. So it's the mass of our sun in something that's about 10 kilometers in radius. And by this, as really visualized in this artist's conception, where here's a neutron star, right, relative to Manhattan. So think of that as, a mass, the amount of mass in our sun in something that small. So on August 17th, this is what we saw in our data from LIGO. And this is now showing something a little bit different form than I've shown you before. This is something we call a time frequency plot. And what it is, on the x-axis is time. So the two neutron stars merge into one at time t equals 0 here. And so before that time, they're orbiting around each other, emitting gravitational waves. And here's the frequency over here. So each little point in this plot is showing the energy in our detector signal at that time and frequency location. Okay, so for example, 20 seconds before the merger, at a couple hundred hertz, there's not much anything significant. But what a chirp will do from the gravitational waves is make this track through this time frequency spectrum, or time frequency map. And this track is in fact that track of a chirp. So the frequency is increasing over time, and it's actually increasing in amplitude a little bit over too. And this is just a nice, very visual way of kind of easily picking out a chirp if the signal is strong enough. And in this case, it was strong enough. So we see, people saw this right away on August 17th and saw, wow, that looks like it's it. We've got it. So the next thing that happened is we saw that within 2 seconds of that, actually, an X-ray detector that's in space, it's called a Fermi Gamma Ray Observatory, detected gamma rays about 2 seconds later. That's what these plots are showing. And Fermi also doesn't have terribly good pointing in the sky, like LIGO. So Fermi said, we have these gamma rays, and they're coming from this patch of the sky, a pretty big patch of the sky. Well, LIGO said, yeah, we're getting gravitational waves from this patch of the sky. And then when we add in the Virgo data, we constrain that to a smaller area right here, and it's overlapping with those gamma ray detections. And then telescopes started to point their telescopes in this region and try to find it. And it wasn't too long before they did. So in fact, the first telescope image came 10.9 hours after this is timed from the time of the merger. So 10.9 hours later was the first image. And what you have to pick up, so this is an image of this big blob in the center is the galaxy in which the neutron stars that merged were in. And compare this image with this image. This is an image of the same part of the sky that was taken, it says here -20, so 20 days before the merger. And what you want to look at, it's marked by these two little marks right here. So 20 days before, in this little region, there was nothing. And then 10 hours after our gravitational wave detection in that region, there was a nice, this telescope saw a nice image there at that spot. And then many other telescopes looked at the same area and saw the same thing. Oh, we're getting actually some audio. And this event, all of those electromagnetic observations that have been made are collectively known as a kilonova. A little bit of a dramatic music that goes on. But this is now an animation of that whole process that went on. So it's the neutron stars merging and then ejecting all kinds of material, emitting not just gravitational waves, but gamma rays. And then one of the other interesting things about these neutron star mergers, as the heading here says, it's a foundry for the universe's heaviest elements. So what happens is some of the mass, so a lot of the mass of the two neutron stars, right, they collapse and they form another neutron star that then probably collapses to a black hole. But some of the initial mass gets kicked out from that, and in that process there's a lot of energy there, and those neutrons interact with each other and they form various elements, heavy elements that we know of in the universe. And the ones we often spout are gold and platinum get formed in these events. So in fact, all the gold that we have here, that we mine up here on Earth, was presumably created by a neutron star merger, X billion years ago. That's one of the reasons this, it really captures the imagination. So let me just kind of wind up by just summarizing that, we've launched this new field of gravitational wave astrophysics. We've made the first direct observations of gravitational waves. So far, we've confirmed that that Einstein's theory of general relativity explains very well what we've seen. We'll keep doing that as we make more measurements, and we can test it even better and better. We now know that the binary black holes of this exist out there in nature. We didn't know that they actually existed before this, and we've observed binary neutron star collisions for the first time. For me, being the instrumentalist, maybe the biggest thing is actually, wow, these machines that we designed and made work, designed to work at this 10 to the minus 21 level, actually do work. So for me, that's one of the biggest accomplishments. So we've turned on this completely new sense in which to study the universe, and whether it's just gravity alone or gravity and light, we've got this new tool for making new discoveries, and I think we'll keep making more. So, thank you.
That was Astrophysics for Dummies. I think you all enjoyed it. Thank you, Peter. We were really able to understand most of it. There'll be a Blue Book exam. It's under your seat. But Peter, would you like to sit down? And now we're going to have Andrew and Zabi join us on the stage. Does everybody have some water? And we're going to have a thoughtful conversation. And I will join you. Does everybody have a microphone? Are you sitting on yours?
Oh.
Test.
Testing. Good.
Test.
Before we begin our conversation today, I would like to thank three unsung members of the NYU Tandon administration. Nilsa Marin, who's not here. She's going to meet her for dinner. Brad Panul, Chief of Staff. Brad, you want to raise your hand to the Dean, if you're here, and Associate Dean for Special Projects, Tishrini. And Jason Weicker. Is Jason here? Okay, well, they're all working on their next activity, but it could have happened without them. And my executive assistant, Caroline. Caroline, I know you're here, so will you raise your hand? And this is Caroline. And can we have a round of applause for all four? Also, I'd like to recognize another guest here today, Mr. Richard Preston, noted author and essayist. Richard, with the bow tie, raise your hand. It was his profile of the Chudnovskys and their mathematical algorithms in the March 2nd, 1992 issue of the New Yorker magazine entitled Mountains of Pi that ultimately created this lecture series. That's another example of how small acorns create great oak trees. And I thank you, Richard, and see what you've spawned here. So it's great, and thank you. Round of applause. So this afternoon we have Professors Andrew McFadden of NYU and Zabi, did I say that right? Marca of Columbia University. By the way, are your wives here? No wives. Okay, I was going to introduce them too. Who have kindly agreed to join us on stage to participate in a conversation with Peter about his remarks and his work. And I'm going to call you Andrew. is an associate professor at our own NYU Center for Cosmology and Particle Physics, and his work on models to explain the explosive death of massive stars and the growth of black holes from stellar collapse are some of what you just heard. He graduated with a BA in astrophysics from Columbia in 2000 and earned his PhD in physics from the University of California at Santa Cruz, and his dissertation was Collapsars, Gamma Ray Bursts and Asymmetric Supernovae, which is what we just saw. So I really feel good that you're here today. And he's had research appointments at Caltech, the Institute for Advanced Study, Harvard University, and has received numerous grants. We like that at NYU. Yeah. Keep up the good work. From the National Science Foundation and NASA, and has been the author or co-author of over 70 research publications at over 90, and has participated at over 90 international conferences. He is a recent recipient of numerous awards and fellowships, including becoming a fellow, a Kavli Fellow. I don't know if you knew that, at the National Academy of Sciences. And he has an unusual career path starting as a public school teacher. And that's important because when you graduate from here, you're going to wonder what are you going to do for a living, right, Orion? And you do whatever you can do to pay the bills, and that's obviously what he did, but he's going to explain that a little bit later because that's the path. You just never know which path you're going to be taking. Professor Marker received his PhD from Vanderbilt University before moving to Columbia. He had a research career in experimental particle physics at Cornell University, and then at California Institute of Technology working on gravitational wave detection. He holds the title of LaCroix Professor of Physics at Columbia University and is a recipient of the Blavatnik Prize for Achievements in Astrophysics and Biophysics. Michelle, are you here? And Michelle came especially because your award from Blavatnik, because he's a very big supporter of the New York Academy of Sciences. And you are the author and co-author of more than 350 peer-reviewed scholarly papers. I don't know how you've had time to write all that and do your research, but that sounds like a lot. Yeah. And served as a reviewer for agencies that include both the National Science Foundation and NASA. And he has worked on comprehensive contributions to gravitational wave astrophysics at LIGO. So I guess you two have known each other. Wow, I guess I should speak it to the... Can everybody hear me before? I don't have to repeat, but okay. So you two have worked each other. Now, how did you communicate with each other?
Email.
Email.
I mean,
we see each other at least a couple times a year at various meetings. Yeah.
Yes, and Peter had been an inspiration for me. So probably he doesn't know, but he's the top experimentalist in my age group. So I think you had been a great effect on me. I don't know. I never told him.
What's fascinating is that, can you imagine getting communications from 1,000 people every day? You get emails like 10, 15, 20, 30, 100. I don't know how you organize all that data, but we'll get to that. Yeah. And so I thought what we'd start with is some questions. Maybe, Zabby, you want to start with a question for Peter based on your experiences with Peter or in this area?
Yeah, so it's very funny. I just realized it sitting there that Peter's mentor was Ray Weiss. Andrew was inspired by Kip Thorne. My mentor was Barry Barish. So it's a very strange group of people.
I've got all three.
I spent a lot of time in the lab in Louisiana with Ray Weiss, hearing very interesting stories. But you know more. Can you tell me a very cool anecdote from Ray? What you can tell?
Oh gosh. So he's asking for a good Ray story. Yeah, let's see. Let's see. I mean, I'll pick up a story that a recent story that he is involved with regard to these. So one of the things that Ray spent a lot of time on, which you might not guess, being something a physicist, MIT physicist would spend his time on, in terms of when we first constructed the LIGO, the two facilities. He ended up choosing to spend a lot of his time on the design of the vacuum system, and in particular those long beam tubes that were shown, the 4-kilometer beam tubes. And like I said, that's a bit, you might think, okay, that's a job for engineers, mechanical engineers, etc. But Ray spent a lot of time on that because he knew that the vacuum system had to be done very carefully, right? And we were also trying to do it, we were trying to build that long vacuum system we didn't have a lot of money to do it, okay, let's put it that way. So we had to do it in a fairly cheap way. So we did it in a different way than, like a high energy experiment like at CERN would build it, and they just put a lot of vacuum pumps on it to get to the pressure level that they needed to. Well, we couldn't afford all those vacuum pumps with the money that we were working with. So we had to construct those beam tubes in a way that we could get the low level of vacuum that we needed, but in a fairly inexpensive way. And what that means actually is it's actually kind of remarkable to think about. We've got these 4 kilometers long tube, and we only have vacuum pumps at the ends of that tube, the two very ends. And we're getting the vacuum level that we need throughout that. And a lot of that was done, he worked with Ray but Ray was very instrumental in working out a way of, one of the things that happens in vacuum systems like this that you have to deal with is hydrogen that comes out of the steel can limit the pressure. And again, in many high vacuum systems you deal with that way just by having big pumps that can pump that hydrogen out. Well, we didn't have the big pumping capacity. So we worked through this process to process the stainless steel, in a particular way to anneal it that would drive the hydrogen out of it before they made the tubes, so that you didn't have as much hydrogen coming out. They spent a lot of time on that. And then I'll round it up with kind of more recent discovery. You can imagine, how do you look for leaks in a long vacuum system like that? And it's important that it doesn't have any leaks, of course. Well, recently we did have actually some leaks show up particularly in the Livingston Observatory. And so again, he was very involved in figuring out, okay, you've got this, this long vacuum, long tube, 4 kilometers long, you've got a leak along it somewhere. How do you figure out where it is? And so he worked on some of the algorithms about, you can measure, close a valve here and there and measure pressure rises and, do some localization of where it is. And with that, they eventually, with some of those ideas, they eventually tracked down some of these leaks. And it's actually interesting why they were formed. Why initially the whole thing was constructed didn't leak. So over time, it had developed these leaks in stainless steel, right? So stainless steel is not supposed to rust or anything like that, right? So what actually happened? Again, it's a little bit of an interesting story. A couple of things actually happened. They determined, and again, I bring it up because it's one of the things that Ray was just spent a lot of time just thinking about. So one, we thought that there was corrosion on the tubes down there in Livingston from mice that lived in this enclosure, and in particular from the mice urine that would be on the tube, and it would react with other things on the beam tube. And then eventually, that's probably one of the causes, but then eventually, actually later it was found probably even a more important cause were little bacteria that end up, there's a particular kind of bacteria that essentially eats stainless steel. And we think we had some of that in the system at Livingston. And so I bring it up because the whole vacuum system, I think, is a very interesting engineering project all on its own. And it's something that Ray is one of the experts on. But you don't really think of, that the physicist who kind of conceived of the grand notion would be, get his hands dirty at kind of that engineering level. But that's the kind of physicist he is. So yeah.
Yes, and it costs $200 million, so it better be good.
Yeah.
Did you, Andrew, want to ask a question?
Sure. It's amazing that LIGO detected 2 black holes orbiting each other and merging, and then it was improved and detected 2 neutron stars merging, which is really exciting. Do you think we'll see a black hole and a neutron star merge?
I mean, I think we will. I don't think, I think with both of those, black hole, neutron star, we expected at some time to see both of those. We just didn't know, how many are there out there. And same thing for neutron star black hole. There's no reason not to think that they're not certainly going to be out there in the universe, but just how many there are at this point, we don't know until we start detecting them, and then we'll be able to say how many there are. So, yeah, I do think eventually we'll get there.
I'd like to follow up on the comment of symmetry that was made by Ms. Boylan. I guess she's out for right now, but she'll be back as I see her purse there. So when Ed Witten was here 20 years ago, he talked about the potential for string theory and a grand unified theory, and the possibility of an answer to the general relativity law, if it really works. And you said that Einstein finally became quiet about it. Now, your work supposedly has an impact on that law, and do you see it helping Ed Witten to answer his lifetime question about string theory? How do you see this impacting string theory? And then I'm going to ask each one of you if you have an opinion too. So you're first.
Yeah. So I think at this point, we're not saying anything about string theory. And I think, so just to step back a little bit, I think what Ed was probably talking about was one of the things that people have been trying to work on since Einstein. Einstein's theory of general relativity does a wonderful job of explaining everything that we observe. What people have tried to work on since then is to, the other sort of great achievement of 20th century physics was quantum mechanics. Explaining things at the atomic and the nuclear level. So what people are trying to work on since Einstein is marrying those two theories, quantum gravity. So far what we've been measuring doesn't really say anything about quantum gravity. And it's certainly not my area of expertise either, so that's about all I can say about it. So
Okay.
See what other expertise there is here.
Before I let you answer, the question I want to ask was, where's all that platinum and gold going to that you said was being created?
Yeah, so it's created in that neutron star merger, and then it's eventually, all that matter is eventually forming planets, eventually, down the road, and so.
Made of gold and platinum, these planets.
Partially, yeah, exactly, yeah.
Wedding rings.
Yeah.
So
it's an interesting idea, right? Where does the stuff, stop to think, where does it come from? Because it wasn't there right at the beginning of the universe, just had, elementary particles. Where did the actual gold and platinum that we mine actually come from? I think this is it.
So, Zabi, how do you see this discovery or these discoveries impacting your future research and career? How do you either take the information? Has it impacted your thinking about how you might want to change your research? Why don't you tell us a little bit about how you see this impacting you personally?
Well, it just vindicated me. So when I joined the LIGO collaboration, people told me that I'm totally crazy. This thing will go nowhere. I just throw away my science career. And I told them, no way, it will detect gravitational waves. And we detected gravitational waves. When I joined the LIGO project, I started up another crazy thing. I thought that multi-messenger observation, namely observing gravitational waves with light, neutrinos, and other things, will actually lead to great science, like where is the gold coming from? At the beginning, nobody believed me, but as we got closer and closer to today, people believe me. So now I'm in an existential crisis because other of my dreams became true. So now I have to think about third-generation detectors. And I'm fairly sure that Peter is also thinking about the next generation of detectors, because we are seeing a very small portion of the universe. We want to see the full universe. We need a more and more sensitive detector. We need to see more, because if we see bigger fraction of the universe, we will see the holy grail of gravitational waves, the unknown unknowns. We had seen things we predicted. We had seen binary and spirals of black holes and neutron stars. Those were the sources we saw LIGO on to National Science Foundation. But the really big surprise what Peter actually is finishing his talk is the source we didn't think of. Wouldn't that be cool?
Andrew, and how do you see this impacting your work in the future?
Oh, it's a huge impact on my work. I'm a theoretical astrophysicist, so I study things like neutron stars and black holes and how they interact with each other. But what I do is I use computers to simulate how neutron stars interact with black holes, for example. And so now that there's actually data, so we can actually see black holes and neutron stars merging, it's incredibly exciting because that constrains our models. Most black holes in the universe are very far away, and it's hard to detect them. But with LIGO and also seeing light from neutron stars, it constrains models for how neutron stars merge, how gold and platinum are formed, how it's distributed in the universe. It's extremely exciting, and it's completely transformed my research.
That's great. Career paths. Remember, we have a lot of students here, so I'm going to focus not only on the present, but really the future. So you started 25 years ago with your lucky PhD thesis. What advice do you have to give to students here today if they want to be in astrophysics? Where should they go? What should they do? How should they start?
Well, I would say, I mean, I was motivated by, the thing that interested me, and I said at the beginning of the talk, I was really attracted to this, at the time, a very nascent field, but very sort of very grand objective. But I wasn't necessarily in it. Again, I had no idea how long it was going to take or anything, and I wasn't necessarily in it to actually get to the final objective. But for me, it was, even just from the very beginning, it was a very just interesting thing to work on, just the design of the detectors. And I would say, so for me, it was just, if you find yourself working in a problem that you find interesting, then that's what's going to keep you going, I think. So you don't necessarily need to know where it's going to lead to. But I think if at any one time it's, you find it interesting to work on, and that there are challenges there for you, and that the other part of it is, I think, again, for me, I was always working with interesting people, found smart people to work with. So I think if you find yourself in that kind of environment, you're not going to go wrong. But
Now I'm going to conclude by asking you two, but say that after they answer, we are going to adjourn this part of the lectures and have people come up if want to meet our lecturer and our interlocutors. But first, why don't you answer? And maybe you want to talk a little bit about your experience as a high school teacher. I'm not sure. I don't want to, but go ahead and tell our friends here what you recommend for them.
Okay, well, don't give up. That's the most important thing. I went to Columbia. I studied astrophysics, but I wasn't quite ready to go to graduate school when I graduated. And so I worked as a school teacher in New York, and I was actually on the subway, on the F train every day, and I read physics books. That's what I did. I solved problems every single day. It was 3 hours a day, every day. And that was really important. I just was interested enough in it that I got into it. And then from working as a high school teacher, then I got a job at Harvard where they were interested in science education. And I took classes there just on my own. And that was for many years. And I didn't go to grad school until I was 28 or something, which was considered very old. And so, people said you'll never get in, that kind of thing. So but I wanted to do it. And so I persevered and I kept on trying. And so the point is that even if you have dimples or your path isn't straight and narrow academically, it's still possible. You just have to not give up, be dedicated, try really hard, and things can work out. And so I'm really glad that I persevered.
So my advice is that if somebody tells you it's impossible, go for it. They are wrong. So I will tell you a few stories about students we actually worked with in LIGO. So Alexa participated in actually commissioning and switching on one of the interferometers, part of the team. She's working on quantum computing in California right now. She's fulfilled. Maria was working on black holes. Now she is working at JPL. Maria Carisi. Peter Kalmus was working on multi-messenger astronomy. Now he's doing climate science at JPL, and one of our colleagues is actually working at SpaceX. He is responsible for significant part of the spacecraft. So when you work with LIGO and gravitational waves, pretty much everything is open. Go for it.
So in conclusion, it's P cubed. Passion, perseverance, and ignore the possible and shoot for the impossible. And I want to thank you once again for being with us this year, and a round of applause for our friends down stage.